important. So dimension of R over Q. So these are vector spaces, so we can talk about dimension. We want to show it is infinite. Right. One very easy way is to just by cardinality you can do, right? In fact, you can say more precisely, this cardinality is same as cardinality of R. Okay. So we have proved earlier long time back that every vector space has a unique, the cardinality of the basis. I mean, there is a concept of dimension and it's a unique cardinal number. Okay, that we know. Means any two bases, there is a bijection that we know. So the left hand side is a well-defined quantity. Now, first let me just tell you sketch the cardinality proof, and then whatever proof Arnab is saying, we can think about that. And then there is also should be a third way, which is basically using field theory. Which is yeah, we will talk about that. That can also be done using field theory. Right. But first we do this minimal polynomials and things like that. Using cardinality. So using cardinality arguments, using cardinality arguments. So how will that be? Well, let bi be a basis. Using this, we want to, what does this mean? This means that bi is in R and finite linear combinations of bi's will give you finite q linear combinations of bi will give you every element of R, right? That's fine. So if I should write that, I will write like this. Bi qi bi I from 1 to n. N is in naturals. This stands for finite linear combinations. Yeah, maybe I will write J. Okay. J is in I, Qj is in Q. This is the meaning of finite linear combinations. Finite Q linear combinations. Okay? N is also changing everything. Q is also varying in Q, J is varying from that thing. Okay. And this is a claim. Let's quickly get over this claim. I should also just write that this is the dimension. By definition, right? This is the dimension of I. So this is equal to R because it's a basis. Okay. What is the cardinality of LHS?
तो हमने I क्या है?
Huh?
I
I, yes. So I is an indexing set. I is just used to index these bases because you want to say na B1, B2, B3. So in this way, I will be natural numbers. Correct? But I cannot say like that because I don't know the cardinality of BI. Is it fine? Is that fine?
yeah, okay.
It's a, you understand when you have some collection, you want to index it. So you want to relabel it. You have to go outside natural numbers sometimes. So you just, and this I will be. Now this is, you should, both of you should check it later. What is the cardinality of LHS? And I'm already telling you it is just Q. Sorry. Wait. How can I say it is Q? Certainly not Q. I want to say it is I, but I have to convince you. Yeah, let's see. Yeah, so prove that it is I is equal to cardinality of I. Okay, this you should try for homework. And the intuition is that it is like taking finite subsets of your set, right? If you fix the n, that's a finite subset of fixed cardinality. Fixed take n equal to 1 first. Then it is basically I times Q. But cardinality of I times Q is same as cardinality of I. Because I is at least Q and Q cross Q is Q. That's I cross Q will also be I. You can prove that. Okay. So this using that kind of argument and take n equal to 2, 3, take the union. Okay. It's not completely trivial, but please try it first, then only you can know what is it that you say. So this gives you one solution, right? Yeah, because cardinality of RHS is R. So assuming this implies that cardinality of I, which was the cardinality of the basis, is equal to R. So it's not just infinite, but it's in fact same as cardinality of reals. Okay, this is a very prototypical standard cardinality argument. There's nothing very strange. Fine, try this and then now let's move to the argument which Arnav is saying. So maybe I will just write, yeah, dimension. Yes, Arnav, please say what is the.
तो पहले कॉन्ट्रडिक्शन से प्रूफ करने के लिए दे टेक एज्यूम कि डायमेंशन ऑफ R over Q is n less than infinity.
Okay, ठीक है, less than infinity.
Then we have to find n plus 1 linearly independent vectors in R over Q.
Okay. Okay. Q independent vectors in R. But yeah, what you said is the same thing I've written. Okay.
Hmm.
Okay. Then how do you find it?
Then they took P1, P2, Pn plus 1 first prime numbers.
Okay. Okay.
And then took log of P1, P2.
Yes.
Why
So
they took, I don't
yeah,
know.
they're taking log to get some irrational
Sir, I
numbers.
think it should be n plus 1.
Yeah, n
Right.
plus 1.
Yeah. Otherwise, we will not get correct. Right. So they are taking log to get some irrational numbers. Okay. That is the thing. And now you should ask, why are you taking irrational? Why do you want to get irrational numbers into the picture? Okay. So that is because if you take an irrational number, like let's say if you take the simplest case, if you take root 2, okay, and then if you take the vector space generated by Q, you take this thing, which you understand from field theory or even just direct. This is just A plus B root 2. You
Hmm.
can take that definition. Then the dimension of this over Q is
Will be 2.
will be, so you know that, and you can prove it easily. Even if someone doesn't know it as a theorem, you can easily prove it. And this is the reason. Okay, so if you take more and more irrational things, if you take nth root, then I suppose you should get n. Okay, and this already gives you a proof, I think. But let's listen, but let's see what argument. So you understand why irrationals are being taken, right? Okay, that is the point. So you see, just to make a very small comment, this is the, now you will start to appreciate linear algebra more, because if you want to say that something is irrational, or if you want to say something is more irrational than another, or if you want to say something is like very like infinitely irrational, like you want to say transcendental, to express these things, the language of linear algebra, the language of dimension, helps you to express these things mathematically. Okay. As you can already see some small instances. Saying that pi is transcendental is the same as saying that the vector space Q adjoint pi, that is a vector space over Q, that's infinite dimensional. That's the same statement. Okay. Yeah. So anyway, so what's the argument? Let's see.
Then they took linear combination of these numbers, A1, NLP1, like that.
Right.
Yeah, now okay, then they take AIR belongs from the Q, rational number.
Of course, right.
So they write it as like JI by KI.
Okay. Okay.
And then they multiplied that number with K1, K2 to Kn plus 1.
Right. So you
Just
want
to make it integer.
right. So you want to get integer combinations, right? That's another, that is also a point that you should pay attention to. Okay, that whenever you have a linear combinations over Q, you also get linear combinations over Z. So that point will be very useful soon when you do modules over teachers. So yeah, so we just assume that AI is in Z. Okay. Yeah. And now you are done, right? Just take properties of log.
Yeah, then it's done.
Right. So actually, so I was slightly wrong, and I think I was wrong when I said that they want to make it irrational. Right? That's not what they're doing. They're just using the unique factorization of arithmetic. integers, right? No? Is that not correct? Yeah. Aryan, so this is
But,
probably related to your function, kind of. I don't know. You can see it.
But Shubham,
So,
last time,
sir,
one last
did you?
time.
Yeah, and I was saying that, like, Aryan, so yesterday you sent me a function, arithmetic function, right? There was no log, but it was
Oh,
similar, and it's that
yeah,
this is
yeah.
also using the
Very similar.
unique factor. Yes, and log is the natural thing to consider, but you have considered what you have considered, so now you have to explore based on that. Yeah. Yes, Aryan, what were you
Yeah,
saying?
yeah. Yes, sir.
Sorry, Arnab, what were you saying now?
No, I was
I
asking.
was
Did you?
Huh. Okay, cool. So let's, it's done,
I
right?
was asking ki just one more time, then why we took ln, please.
Yes, because no, you just continue the steps and then you will realize. So I think this is a very clever proof.
No, proof is okay. I'm asking that why we take log. I mean,
Yes, because you take log to convert the, if you want me to put it poetically, they take log because they want to convert additivity into multiplicativity, so as to use the unique factorization of reals. Right? You get this product, right? Factorization. And by unique factorization, you know that every number has a unique factorization. And so this number is equal to 1. And 1 has a unique factorization, so it means that all the AIs are 0. Okay? This is 1. And of course, you're using the log is an injective function. Right? That's clever. I mean, it's a nice proof. Yeah. But this log, these tricks are used because, I mean, log is the way to go between, whenever you want to go between addition and multiplication, you either use exponential or log. Okay. So this is the second proof. And we already saw the third proof, but let's say that rigorously, so we have two proofs. That's nice. But you see, I mean, you must realize that this proof is stronger. This proof I gave first in the beginning, the cardinality argument, it is stronger. It shows that it's R. But this part requires a lot of some work with infinite cardinalities. Okay, if you're willing to do that, then you will get that. But one thing I would say that these cardinality arguments don't go very far. Okay, after some time they will. I mean, either if you show that something is very big or something is very small, cardinality argument will work. Okay, but if you want to show something is in the middle, something is, then it will not work. It works in the extreme case. It gives you a cheap proof. Okay, kind of, yeah. But this is much better, I suppose. But let's just give a third proof. I mean, maybe you can, yeah. Let's see. Yeah. Want to say this is infinite. So the case for C is also proved. I don't think there is some easier proof in the case of C. Well, there will be, but we don't need to because R is contained in C. So in C, what will happen is maybe you can take some exponential function and, I don't know, get some easier proof. Okay, but let's not talk about that. So this thing, and so first maybe I should say, because this is elementary, something that you can do, and this you should do, and maybe we can think about other creative proofs of this thing. Dimension of Q of this thing, Q adjoint this. Okay, this is N. Again, I will not try to prove it at the moment. It's not difficult. You should try it. So what is the idea of the proof? The idea, technically idea, I'm not giving intuition, you already can feel it, I suppose. The idea of the proof is, you can do it as a Olympiad style also, I suppose, but if you just want to do it formally a little bit, you can just try to prove that this is a field, right? It's a ring, it's a field. It's a ring to begin with. So this ring is the same as this ring. There's a ring isomorphism. You can prove that. I mean, it's N. Okay, and that ring isomorphism hence is also a vector space isomorphism. You can prove that. Second thing, and then you try to tell what is the dimension of this vector space. That's not very difficult, because it will be generated by 1 x square till x to the n minus 1. Right? This will be the Q basis of this vector space. Okay, that you can see because just write polynomials independent. Okay, that's the third proof. And I've not proved anything. You have to, but I've told you the sketch. And this you will find in any field theory chapter. The beginning is start with this. For example, you can look at Hurstein. I remember is there this exact thing, Hurstein algebra. But you should first try it. And when you learn the field theory, you will automatically prove this. You will not have to think. The other thing which I actually don't know how to do, unfortunately, is I don't know how to prove this. And this would be, so this does it, right? Because if you change the n, you get that it's larger and larger. Okay. But what I don't know how to prove, because I've never learned this. Means I've read this once, but I don't remember. No, I've read it for E. Yeah, maybe you can read for E also. This dimension is infinite. And this infinite, I mean, this is equal to n. Okay. And of course, this is the same thing as dimension of Q at joint E. So maybe one of you can read this and tell me how to present this, so that we can know how to do this. Okay. So you can first see the significance of this statement that this. So, yeah. So what is this really? What is this? Okay. So this thing no, I'm sorry. You can. This is true. This is not false. But let me not write it like this. It's not false, but to write it properly, you should probably not write it like this. Because we don't need the field structure in this case, and they differ. Okay, so this is basically take pi and evaluate it at all polynomials. Okay, all rational polynomials. Okay, and the claim is that the dimension is infinite. Okay, let me tell you the significance of this statement. It's quite a significant result. It's same as saying that pi is transcendental. Okay, it's not easy, not hard at all. You look at this following thing. So you look at QX, your favorite ring, and what should we write this side? I mean, okay, so maybe I'll just write this Q at joint pi. Okay, and then you take what you say is, okay, I will send 1 to 1, and I will fix Q. I will send Q to Q, and 1 to 1 will say Q to Q, send X to pi. This is a ring, both are rings, and this is a ring homomorphism. And hence it's also a vector space homomorphism, because A plus B and so on, this thing. Now, what does it mean to say pi is transcendental? Pi is transcendental. Pi is transcendental over Q means that there is no, this is the only natural statement. You cannot say pi is transcendental over R. That's nonsense. Right? Because, of course, because pi x minus whatever x minus pi is a polynomial whose 0 is pi. So that doesn't make any sense. Pi is transcendental over Q Okay. What does this mean? This just means that given any rational polynomial, pi is not its root. Right? Pi times that is not 0. Correct? So if you assume that pi is transcendental, which people, I do not know the proof, but I assumed it a lot of times. I read it once, but I don't remember at all somehow how it went. Okay. But if you assume this statement that pi is transcendental over q, I've told you the definition. This means that this phi is a, so translating it to, because you can say all these fancy things, but want to prove it or disprove it or use it, you have to say it in the language that you're talking, and that's ring homomorphisms and things like that. So that basically says that this phi is a bijection, correct? Because it has no kernel. That's the statement. Same thing, right? Because kernel is precisely some polynomial p such that p pi is equal to 0. Correct? So that doesn't happen because pi is transcendental if you assume it, and if you can try to read the proof also. And maybe I will just call it evaluation at pi. Okay. Is an isomorphism. Okay. And how does it help us in our problem? Well, it means the vector space dimensions are same, and this means that the dimension is equal to this dimension of this, which you know is infinite. I mean, it's not just infinite, but it's equal to n. But I just said, okay. This is the. So these are the proofs. Okay. But I don't know how to prove pi is transcendental. Let's just let's see if we have something that probably it will take some time to study. So I will not. Just take 5 minutes and see what's. Yeah, but this may not have pi is transcendent. But let me show you this. Herstein, I think, has that E is transcendental. That's somewhat easier because pi is a very strange thing. I mean, we don't even know a proper definition of pi, I think. Is this the book, Herstein Abstract? Is it called Abstract Algebra? I don't know.
Sir, I don't know about
Huh?
transcendental, but there's one proof for the irrationality, which
Yeah,
is very like, I think Niven's proof.
irrationality is quite easy. Is it Lewin's proof or irrationality? No,
The one,
irrationality. That just comes from the
the one,
expansion. No? The one.
I don't know, but the one I saw was Niven. He uses an integral, and from there he gets from there he
Right.
proves that it's irrational.
No, so I
Like
think
a
he
very
also.
short proof.
I think he also proved this transcendental. No.
Oh, I'm
In
not
that,
sure about that.
Yeah, I think he also proves it is using the integral. That's what I have in mind. Okay, that's it. So this is here it is. Yeah, and about E, you are saying, I think that also proves that it is transcendental. Yeah, but again, I don't find the transcendence of E in this book. Let's stop. Yeah, topics in algebra, not abstract algebra. This is the book. Yeah, maybe we'll look at both of them because this is a topic which I. Let's see. So it's not in ring theory. Then you have vector spaces. Yeah, transcendence of E. Okay, 216. So this is a classic book. There you go. The defining algebraic and
Sir, it's not shown on the screen.
Oh God. Okay, sorry. Yeah, so I'll just share the screen. Then it's easy. Yeah. Okay. So this is a Herstein, right? Herstein. So where we are. I mean, look. irrationality of E is easy. That you should do. That's a standard high school trigonometric. You can find it in your trigonometry book. Okay, transcendence, irrationality of E. Try it. But that's not going to solve our problem because we want an infinite dimensional sub-extension, the sub-vector space, right? Subspace. So that transcendence will do it, as I was talking about. So it's very, if we can read it later. But let's just look at this. So the number E is transcendental. So this is derivatives. Right. So it's not difficult, right? So yeah, so they don't use integral. So the integral thing is probably, as Aryan is saying, it only proves irrationality, right? So perfect. Then maybe Aryan, you can just present us this proof, right? Next day. It's because you can see it's elementary, completely elementary.
Okay. Yes.
Right. So
Yes.
you can have this. So you understand topics in algebra. There you will find this transcendence.
Okay.
So Hurstein, topics in algebra, and
Yeah.
you
So
know
next
where.
class on Tuesday, right, sir?
Tuesday, but maybe you present on Saturday. If no, but will you be available
Okay.
on Saturday? You check it.
I'll let you know, sir. I'll tell you
Yeah,
like
but
Friday.
Tuesday is too early for. So I will just. So you take your time because you may have to go back in the
Okay.
chapter and look at some definitions and such. So okay.
Yes.
Yeah. So you please tell us. Okay, transcendence of E. Okay.
Okay. Yes.
So I will close this because it looks elementary. That doesn't have any hi-fi thing, so it's good. And then let's now use the next 5 minutes and look at the transcendence of pi. Wonderful. So these stand. Sorry, this has only irrationality of pi, but I think I will also prove the transcendence. Yeah. Liouville's criteria would be that Diophantine approximation thing. That you cannot have like this Kronecker, these small theorems, right? Using pigeonhole principle in analysis, we prove these are used. Okay.
Yes. So this is the one I was talking about. This is Niven's
it's about
proof.
pi. Yeah, exactly. Niven's
Yeah.
proof using Liouville's criteria. No, they use the integral because there is no other definition of pi. I mean, define pi, you kind of use that's a standard definition. Trapped. Yeah, so that's a perfect thing. So yeah, so why don't you present this also, right? Not much. I just right.
Okay. Yes.
So you
Yes,
can do
yes.
that. This is perfect.
So this is which algebra?
Wait. Yeah. So it's irrationality of pi, and it's all easy. So you can find
Okay.
this irrationality of pi, and you present Hurstein topics in algebra. No, abstract algebra.
Abstract algebra.
So
Okay.
you can
Yes.
note it down. And so Saturday, take your time. In half an hour, 15 minutes, you can, like, all the details are not new. You can plan it and present. Right.
Okay.
That will be
Yes.
good, right? So then we can learn. Is that fine?
Yes.
Okay. So that's cut out. And now let's meet on after this, and then Arnab, whatever is there, we will talk about it. Okay. Yeah. Let's meet
So
after.
and one
Yes.
more thing. So I sent you the mail regarding the
Putnam, and there is another. I think it's related, right? Yeah.
Related. Yeah.
Yeah.
So I think that's interesting.
Okay, good. Then I'll look at it certainly. Actually, I'm
Okay.
also
Okay.
stuck
Yes.
with this other things which I'm reading. So
Okay. Yes.
yeah, I will certainly today. I will have that. There is enough time. It's only that I don't find the motive. Like I have to. I suppose there is no lack
Right,
of
right.
time if we really put our minds right. But yeah, we are, at least
Yeah.
me. Yeah. So let's meet in
Yes.
7-8 minutes, and then we will continue.
Okay.
Okay. This Zoom.
Yes.